Hello and welcome. In continuation with our series of non-aqueous solvents, we have discussed the various types of reactions which take place in liquid ammonia as a solvent. Moving on to advantages of liquid ammonia as a solvent, liquid ammonia dissolves all alkali metals without reacting with them. These dissolved alkali metals can be recovered from the solution by evaporating the ammonia alkali metal solution. Alkali metal ammonia solutions are good reducing agents because of the presence of mobile ammoniated electrons and can be used for reducing materials which are soluble in liquid ammonia. So, these points we have already discussed in our last slides, that the solutions of alkali metals in liquid ammonia are very good reducing agents. So, therefore, this is a very good example of an advantage of liquid ammonia being used as a solvent. Hence, these solutions can be used where water cannot be used as a reducing agent. Ammonia has a lesser tendency to undergo solvolysis reactions with dissolved solutes as compared to water. So, water can undergo solvolysis reactions, water can be hygroscopic, water can undergo decomposition reactions with many other dissolved solutes, but ammonia has comparatively a lesser tendency to undergo such reactions. Now, once liquid ammonia as a solvent has advantages of its being a good solvent, there are certain disadvantages associated with liquid ammonia as a non-aqueous solvent. Since the boiling point of liquid ammonia is minus 33 degrees, so while working with this solvent, lower temperatures have to be maintained along with higher pressures, and these lower pressures and lower temperatures are difficult to achieve. The use of liquid ammonia as a solvent and as a medium of reaction needs special techniques. Liquid ammonia is hygroscopic in nature. To avoid its contact with moisture, the reactions in liquid ammonia need to be performed in sealed tubes, because liquid ammonia, as we all know, is a non-aqueous solvent and it is used for a number of organic reactions wherein absence of water is required. So, the reactions need to be performed or carried out in sealed tubes or in an atmosphere of nitrogen where oxygen or water or air should be absent. Alkali metal ammonia solutions can be evaporated to give the free metal. Alkaline earth metals, on the other hand, on evaporation give the hexaammoniate ion, where M is the alkaline earth metal. Alkaline earth metal, that is a group 2 elements which include beryllium, magnesium and so on. They produce hexaammoniate ions, whereas alkali metals in ammonia can be simply evaporated and they will give the free metal. That means we will get ammonia from a solution of ammonia, we will get sodium from a solution of sodium in ammonia, whereas we will not get magnesium from a solution of magnesium in ammonia. Instead, we will get a magnesium ammonate complex. All metal ammonia solutions, upon standing or in presence of a catalyst, undergo decomposition to give hydrogen gas and metal amide. The solutions of metals in liquid ammonia are strong reducing agents. Metals which have low ionization energies, low sublimation energies and high solvation energies like alkali and alkaline earth metals or aluminium, europium and ytterbium readily dissolve in liquid ammonia to give metal ammonia solutions. So, metal ammonia solutions are specifically only for such kind of metal ions which have low ionization energies, because low ionization energies means that they can lose electrons easily, and that is why they will dissolve in liquid ammonia only when they are able to release electrons in liquid ammonia. The dilute solutions of metals in liquid ammonia are blue in color, whereas concentrated solutions are bronze colored. This is just a small summary of whatever we have discussed till now. The blue solutions are very good electrolytes. The absorption spectra of these blue solutions are alike irrespective of the metal. That means whatever the metal may be, whether it's sodium, whether it's potassium, whether it's magnesium, any metal, whichever is soluble in liquid ammonia, the absorption spectra will be the same. That is, the color, the blue color of metal ion in liquid will be of the same intensity. The bronze colored solutions have an electrical conductance similar to that of free metals. Metal on reaction with n moles of ammonia will give hydrogen and a metal amide complex. This particular reaction proceeds rapidly in the presence of catalysts like ferric oxide or platinum black. The dilute solutions of metals in liquid ammonia, which are blue in color, are paramagnetic in character since they contain free unpaired electrons. In bronze solutions, the magnetic susceptibility decreases because in bronze solutions the concentration of metals is high and free electrons are less in number. However, in concentrated solutions also the electrons are free, although they are less in number, but there are free electrons. As we can see, metal which releases free electrons. In dilute solutions, the electrons and the metal ions are solvated, or as we can say ammoniated to be specific, with liquid ammonia. So metal ions with X moles of liquid ammonia give metal NH3X, and electrons with ammonia give the electron NH3 complex. The electrons in metal ammonia solutions occupy the cavities in the solvent surrounded by ammonia molecules whose protons are oriented towards the free electron. However, as the concentration increases, the metal cations are bound together by electrons into aggregates. Moving on to our next important non-aqueous solvent, which is liquid sulfur dioxide. Liquid sulfur dioxide is an aprotic solvent since it does not have a proton. Its dipole moment is 1.6 dBi. Its dielectric constant is 17.3. The dielectric constant value is low but is sufficient for a number of salts to be soluble in liquid sulfur dioxide. Since liquid sulfur dioxide is an aprotic solvent, so salts with slight covalent nature are more soluble. Aggregation in liquid sulfur dioxide is much less as compared to protonic solvents because of the absence of hydrogen. That is, in case of liquid ammonia, the aggregation of ammonia molecules is very high because of the hydrogen bonding, as hydrogen is present in ammonia. Whereas in case of liquid sulfur dioxide, since there is no hydrogen, therefore the molecules of sulfur dioxide are not as aggregated or as clustered as compared to a protonic solvent. The liquid range of liquid sulfur dioxide is minus 75.5 to minus 10 degrees centigrade, and this range is very long and reasonably convenient to achieve. Liquid sulfur dioxide has a very slight conductivity on it. When the salts are dissolved in it, a conducting solution is obtained. This implies that liquid sulfur dioxide is an ionizing solvent. We have already discussed about ionizing and non-ionizing solvent in our earlier lectures regarding non-aqueous solvents. The proposed ionization scheme, or as we can say, this is the auto-ionization scheme for liquid sulfur dioxide, is wherein sulfur dioxide auto-ionizes to give the thionyl and the sulfite ion, SO2 giving SO2 plus SO3 2 negative. This is the case of an auto-ionization reaction where itself sulfur dioxide as a solvent ionizes to give respective ions. Just like we have studied the various classes of reactions in liquid ammonia, a similar kind of classes of reactions are seen in liquid sulfur dioxide also. Acid-based reactions which occur in liquid sulfur dioxide will be the first one which we will be discussing. Any species which is increasing the concentration of SO2 plus or thionyl ion, which acts as an acid, and any species which increases the concentration of sulfite ions, SO3 2 negative, will act as a base. This point we have already discussed, that any species which increases the concentration of positive ions in a solvent acts as an acid, and any species which increases the concentration of negative ions acts as a base. Hence, neutralization reactions are carried out between thionyl compounds and sulfides, because one of them is behaving as an acid and the other one is behaving as a base. So, a neutralization between an acid and a base can be easily carried out. Thionyl chloride or SOCl2 is a liquid, and the thionyl compound is miscible with liquid sulfur dioxide. Alkali metal sulfides are soluble in liquid sulfur dioxide. Many reactions which support this are depicted below. SOCl2 thionyl chloride reacts with cesium sulfide to give cesium chloride and sulfur dioxide. This reaction again takes place in liquid sulfur dioxide as a solvent. Thionyl chloride reacts with tetramethyl ammonium sulfate, wherein all the sulfate units are replaced by chlorine and sulfur dioxide is released in the solution. The above reactions are carried out in liquid sulfur dioxide. They have been followed in conductometric titrations as well and have been found to give typical neutralization type curves. That means in these cases one of the ions is positively charged, the other ion is negatively charged, and the resulting product is a salt and the solvent is retained. So, the above examples are typical neutralization reactions, but indicators cannot be used to follow these reactions, just like we have indicators like phenolphthalein to carry out the titrations in liquid ammonia or in water, as you have all studied about HCl, NaOH titrations and number of other titrations. So, indicators cannot be used in such titrations because all the acid base indicators which are known are protonic in nature, whereas in this case liquid sulfur dioxide is an aprotic solvent and hence indicators will not work in such cases. So, therefore, these titrations are studied only by measurement of conductance. Moving on to the next class of reactions, that is precipitation reactions in liquid sulfur dioxide. Alkali metal sulfides, acetates and thiocyanates are all soluble in liquid sulfur dioxide. Iodides are generally soluble because they are covalent and hence they will be soluble in liquid sulfur dioxide. The trend in solubility of the halides will be iodide will be most soluble in liquid sulfur dioxide, followed by bromide and then chloride, which is the opposite trend as seen in water. And this is because of the difference in the nature, that is ionic nature and covalent nature. Iodide ions are the most covalent, so they will be soluble in liquid sulfur dioxide. Chloride ions are most ionic, so they will be most soluble in water. And to depict this, precipitation reactions are studied in liquid ammonia and some reactions are seen as follows. Aluminium chloride reacts with silver thiocyanate to give aluminium thiocyanate as a precipitate and also silver chloride as a precipitate. So, this is an example of a precipitation reaction which takes place in liquid sulfur dioxide as a solvent. This reaction does not occur in water. Similarly, thionyl chloride reacts with silver acetate to form thionyl acetate and silver chloride is formed as a precipitate. This reaction is used for the preparation of new thionyl derivatives, as in case of SOCH3COO twice, which has been formed, which is thionyl acetate. So, instead of acetate, which if we have any other ion, then a similar derivative with thionyl ion can be formed. Thionyl chloride reacts with potassium thiocyanate to give thionyl thiocyanate and potassium chloride is obtained as a precipitate. Again, these reactions take place in liquid sulfur dioxide as the solvent. Moving on to the next class of reactions in liquid sulfur dioxide, which are complex formation reactions, and some of the examples as we can see over here. Potassium chloride reacts with antimonal pentachloride to give hexachloroantimonate K3SbCl6. This is a complex which is formed only in liquid sulfur dioxide as a solvent. This reaction rather takes place in liquid sulfur dioxide as a solvent. Sulfide complexes can also be formed. Aluminium reacts with sulfide ions to give aluminium sulfide, which is forming a precipitate, and in excess of sulfide ions, a soluble form of the complex is formed. And these reactions show the amphoteric behavior of liquid sulfur dioxide. Moving on to the redox reactions in liquid sulfur dioxide, very few reactions have been studied in liquid sulfur dioxide. One of the example of such reactions is potassium iodide combining with antimonyl pentachloride, giving iodine and antimonyl trichloride and a complex which is K3SbCl5. And such kind of reactions, as we can see over here, in this case potassium iodide contains iodide ions which have been oxidized to give iodine, and SbCl5 reduces. In SbCl5 the oxidation state of antimony is +5 and it gets reduced to SbCl3, in which the oxidation state of antimony is +3. SbCl5 is the oxidizing agent which oxidizes iodide to iodine, and itself antimony gets reduced from +5 state to the +3 state. The next class of reactions in liquid sulfur dioxide include solvolysis reactions. Solvolysis, as we have already discussed, is a process where these ammonia molecules or the solvent molecules break up, and the following examples which depict the solvolysis reactions in liquid sulfur dioxide. Whatever reactions we are discussing or we have already discussed are now taking place in liquid sulfur dioxide as the solvent. So PCl5 or phosphorus pentachloride reacts with sulfur dioxide in presence of the solvent, which is liquid sulfur dioxide. We need a solvent for all reactions because reactions can never take place in the solid state. They all take place in a state where ions are formed. So it forms phosphoryl chloride and along with this thionyl chloride, SOCl2. Similarly, uranium compound UCl6 along with SO2, which is sulfur dioxide in presence of liquid sulfur dioxide as a solvent, forms uranyl chloride and SOCl2, which is thionyl chloride. All alkali metal iodides crystallize out with solvent molecules. For example, if we consider potassium iodide is an alkali metal iodide which on combination with SO2, if it reacts with SO2, it does not form a new complex. Instead, it just crystallizes out, or it forms an adduct, crystallized adduct with sulfur dioxide, as given Ki.4 sulfur dioxide molecules simply get attached to it. And similar is the case with alkali metal iodide, which is sodium iodide, in which 4 sulfur dioxide molecules simply form an adduct with or crystallize out with sodium iodide. Liquid sulfur dioxide is a very good medium for certain organic reactions which require exclusion of water. So, in case of organic reactions like sulfonation, if water is present in sulfonation reactions, then it might result in the oxidation or it might result in explosive reactions. Similarly, bromination in presence of water, if the reaction is to be carried out, then again bromine will be, this particular bromination reaction, bromine is always soluble in carbon tetrachloride, it is never soluble in water. So, these reactions cannot be carried out in water as a medium. Similarly, Friedrich-Crafts reaction, this reaction also requires liquid sulfur dioxide or any other non-aqueous solvent as a medium for reactions to take place. Apart from liquid ammonia and liquid sulfur dioxide, which we have discussed in quite details, there are certain other non-aqueous solvents which can be used, that is liquid HF, hydrogen fluoride, liquid H2S, and liquid HCN. They are also termed as non-aqueous solvents. These are also actually gases which have been compressed under high pressures and very low temperatures to produce the liquid, and therefore they are absolutely free from water. However, liquid HF, H2S and HCN are poisonous. HCl, we all know, hydrocyanic acid, is highly poisonous. H2S is a very toxic gas, and similarly hydrogen fluoride. They are highly poisonous and they have therefore limited uses, whereas liquid ammonia and liquid sulfur dioxide have a variety of uses because they are comparatively less poisonous. They are toxic, but again less toxic than these solvents which have been mentioned here. So there are a number of reactions which can be carried out in ammonia and sulfur dioxide. A number of oxyhalides like phosphoryl chloride POCl3, selenium oxychloride, nitrile chloride, carbonyl chloride, acetyl chloride, they also have been used as solvents. Oxyhalides can also act as non-aqueous solvents because again they are all organic solvents and they are, except for selenium and nitrile chloride, they are and they have uses as non-aqueous solvents, and they can be used for many reactions to be carried out in case of those reactions where exclusion of water is required, especially organic reactions. Organic compounds get easily decomposed in presence of water, and therefore they need the solvents which are totally free or in which water is totally absent or totally excluded, so that the reactions can be carried out easily. And therefore we have discussed a number of reactions as regarding the liquid ammonia and liquid sulfur dioxide as a solvent have been discussed, in which we have seen how liquid ammonia and liquid sulfur dioxide are good solvents, non-aqueous solvents which have exclusion of water, and they are very good mediums for organic reactions and also certain inorganic reactions, wherein certain inorganic compounds also in combination with water, when they come into contact with water, tend to explode. So in those cases also, for example, if we consider the case of sodium or if we consider the case of potassium, in presence of water, sodium metal and potassium metal as such, they are highly explosive. So they are dissolved in liquid ammonia, and that is why we make solutions of these metal ions in liquid ammonia to produce certain reducing agents. That means sodium ion cannot form a good reducing agent in water, but it can form a good reducing agent in liquid ammonia, because liquid ammonia has totally exclusion of water and therefore it will not undergo any kind of an explosive reaction with water. So apart from organic reactions, inorganic reactions also can be carried out in non-aqueous solvents. And apart from the reactions or the solvents which we have discussed in quite details, we have already seen that apart from these, number of other solvents also exist, non-aqueous solvents, in which reactions can be carried out, but they have their limitations, whereas liquid ammonia and liquid sulfur dioxide are widespread and they have widespread uses as compared to other non-aqueous solvents and also as compared to water, which although being a universal solvent has restricted uses in terms of chemical reactions involving organic as well as inorganic compounds. Thank you.